no worries. Okay, can everyone see the slide? Just checking. Okay, yeah, I guess I'll start then. Yeah, so I mean, I'm using slides here, but also feel free to interrupt me and I'll try to write like derivations on the slides. The slides are more just so that I don't forget what to talk about. So today I'm going to be talking about some recent work in the field of truncated statistics. And while the work is like mostly statistics rather than causal inference, I'm really interested in thinking about and discussing where this could be applied in causal inference settings. So probably the easiest way to explain what the field of truncated statistics is about is through this like really old anecdote that is like probably false, but is a very good illustration about Poincaré and a baker. And so the story goes that Poincaré had a baker from whom he bought pieces of bread that were supposed to weigh 1 kilogram. And so Poincaré, being a huge nerd, went home and like weighed every single piece of bread that this baker ever gave him. And it turns out that the average weight was actually 950 grams per loaf instead of 1 kilogram per loaf. And so he goes to the baker and says, like, you're shortchanging me and I should be paying less for these because they're less heavy than you promised. And so the baker says, okay, you got me. I'll like fix this. And so for the next year, Poincaré still weighs his bread, and this time, luckily, the average weight comes out to just above 1 kilogram per loaf. And so you'd think that Poincaré would be very happy, but instead he goes to the baker and says, like, I know that you're giving me bread that I paid for, but you're shortchanging the rest of your customers. And this actually turned out to be true. And the baker says, how did you know this? And the answer is that instead of just looking at the average weight of the loaves of bread he got, Poincaré was plotting the distribution. And the distribution looks something like this, where like what Poincaré plotted is the black tail of the distribution. And so he reasoned that, okay, any reasonable distribution of bread should look vaguely like Gaussian or at least unimodal. And what I'm getting is actually just the tail of this distribution. So the average of all of the bread that this baker is baking is actually much less than 1 kilogram. And this is like one of the simplest examples of the kind of problem that we want to solve when we work with truncated statistics. It's the idea that we're only observing samples that fall within some observation window. So Poincaré only observed samples that were above 1 kilogram, but wants to make statements about the general distribution, or some like what happens if that observation window were not there. Okay, cool. Yeah, so I'll talk about, I guess, again, depending on time, I'll try to talk about 4 kind of sub problems within truncated estimation. And I think Giannis next week will talk about some more, and I'll mention one thing Giannis did in the extensions. So I'll start with Gaussian parameter estimation in the truncated setting. I'll then move to some simple regression classification models, and then talk about extensions and limitations of truncated statistics, as well as what the open problems are, what I think would be interesting looking forward. Okay, so yeah, we'll start with Gaussian estimation, which is probably the simplest problem in the kind of truncated regime. So in this setting, we have a normal distribution with some unknown mean and covariance matrix. And what we get are, like our generative model is that we sample from this distribution. If the sample resides in some set, then we observe it. If it doesn't lie in some set, we throw it away and restart. So the most notable thing is that the learner doesn't actually know that you sampled X and it was outside the set. It just kind of only sees the X's that are in the set. So you're kind of observing samples from a distribution of X sampled from a normal conditioned on X being in some set. And the goal is to just obtain estimates for mu and sigma, the mean and covariance matrix, that are somewhat close to the true untruncated parameters. And obviously, like in the example with Poincaré, you can't just take the actual mean and variance of the observed samples because that's going to give you a biased estimate. And in one dimension, it's kind of clear to see how to do this. And there are a bunch of very classical methods starting from, I think, like the 1700s or something. But as soon as you go to multiple dimensions or like the high dimensional setting, it becomes a little harder. And so this is kind of a nice figure, I thought, from Daskalakis et al. 2018, where they basically plotted samples in 2 dimensions from 2 totally different distributions and basically challenged the reader to figure out which one is which. And it's pretty difficult. Okay, so yeah, I'll start by talking about what, so this is, again, work from Daskalakis et al. 2018. I'll talk about like the general approach to solving these truncated estimation problems, and we'll kind of move to more complicated settings than just estimating parameters of a Gaussian. So the general theme of our approach is going to be maximizing the likelihood of the data using projected gradient descent. And so maximum likelihood estimation is a pretty standard way of estimating the parameters of a Gaussian. So I mean, if there was no truncation, then we could just write like, we could just have our estimates be the maximum likelihood estimates over the collected samples. So you're just, or like this is, I guess, the maximum log likelihood. And for the normal distribution, this has a really nice closed form. And we can solve this form by just taking the derivative with respect to each parameter and setting it to 0. And what we get are these very standard maximum likelihood estimates where your estimated mean is the sample mean and your estimated variance is the sample variance. And that's kind of it. Like there's nothing else to do in the untruncated setting. What complicates things in the truncated setting is that the log likelihood now changes. So instead of just having our likelihood of a given point being the likelihood under the normal distribution, you still kind of have, let me see if I can write it. So you still kind of have this first term that's the likelihood under the normal distribution, but now you have to ensure that your likelihoods that your likelihood integrates to 1. And so now you have this kind of extra normalization term that's pretty ugly. And so just taking logs, the log likelihood that we get is, again, this nice log likelihood of the normal distribution, but now minus log of this normalization function that's unclear how to compute at first. And so notably, this is no longer going to have a closed form solution like in the untruncated setting. Okay, so what's our approach here? I'm going to basically outline the approach in 3 steps. So the first step is going to be reparameterizing.
Andrew?
Reparameterizing. Oh, yeah.
Hi, can you go back to the next previous slide?
Yeah, absolutely. Sorry.
Yes. So here, if someone told you what this value of integral f fn of z mu sigma is, does that help?
If someone told you what the value of the integral was?
Yes.
Yeah, I think that would help. It's a good question. Like I'm kind of just speaking out of intuition because I don't have a proof for it yet.
Okay.
But yeah, but the reason we don't is because we don't observe when something is outside of the set.
Correct. So the reason I asked is, imagine I told you that S is, let's say, a ball of certain size around the origin, and I told you, and you somehow know what the covariance matrix is. You only want to know the mean, and let's say I also told you what the norm of the mean is. So you'll know what the radius is for the mean vector. In that case, you will know what this probability is. What's the probability that you will actually get a sample from within S,
Yeah.
right? Because it's due to symmetry. So in that sense,
Yeah.
I still don't see like why it will help. That's why I asked the question. Like, I mean, how are we going to use that information?
Oh,
But
maybe,
maybe,
so you're asking
yeah.
if I knew this value?
Yes, if you knew this value, how can we use it, for example?
Yeah, so again, this is just intuition because I don't have a proof, but I guess I would start by just like, if you now plug in this value, then your log likelihood has a really nice form. Like if you know the value is like 5 or something, then your log likelihood becomes like the log likelihood of the normal minus 5.
I see. I understand. Yeah, you can continue. Yes. Thanks.
Okay. Yeah, and if I didn't answer your question, I can also try to answer after too.
No, this is great. Thank you.
Okay, awesome. Cool. Yeah, so I'll outline like kind of the 3 general steps to getting an algorithm for finding these truncated parameters without assuming that we fully know the set S or trying to put any kind of hard constraints on the set S, and like basically with minimal knowledge about the truncation mechanism. Okay, so the first step is we're going to reparameterize in terms of T, which is going to be the inverse of the covariance matrix, and V, which is going to be kind of like T by mu, which is the parameters. So here, yeah, I probably should have put like sigma star and mu star on the last slide for the true parameters. Here I'm going to write T and V as like the current estimate of the parameters, not necessarily the true parameters. And so like, I guess just as an exercise, like under this reparameterization, if we have a normal distribution at X, so the previous, when we had a normal distribution, we had something like X minus mu, sigma inverse, X minus mu. Now under, sorry, my writing app completely crashed on me. Okay. I'll try that again. Okay, so now under the new parameters, if we have V and T, our thing is now proportional to like 1/2, and now this becomes, so we had, previously we had like X minus mu transpose sigma inverse X minus mu. Now rewriting this in terms of T and V, we get 1/2 X transpose TX minus 2 cancels out with the 1/2 VTX plus V transpose T inverse V. And that becomes like the new exponential part of the likelihood. And so this is kind of a standard reparameterization. It's not new in any way, and it's like nice for making your likelihood convex even in the untruncated setting. Oh, okay. So then after we reparameterize, the interesting thing is that after you reparameterize like this, we can get an unbiased estimate of the gradient only using truncated samples. So if we take the likelihood that we wrote in the last slide, I guess, okay, it's not going to be many. Okay, so if we take the likelihood we had in the last slide, and then we just take the gradient with respect to V and T, what we're going to get are essentially these 2 functions. And the derivation is pretty simple. It's like probably 1 or 2 lines. And the interesting thing about this is that we can actually calculate all of the quantities shown here only using only using truncated samples. So all we need is oracle access to the set S. We need to be able to ask, like, is this point Z in the set S? Namely, these terms I've outlined here in red are basically like the expected like first and second moment, like under the current parameters, but using the true truncation set. And then once we perform SGD, like this X and XXT are just going to be like the batch first and second moment. And so what we end up with is like a gradient step that we can actually execute using only the knowledge that we have. Okay, so step 2 into we show that like it's possible to execute SGD on the log likelihood, but we didn't actually show that like that it actually works, like it recovers the true untruncated parameters. And so step 3 is exactly showing that SGD will converge and it'll converge to a global optimum, which are going to be the true parameters. And so the key ingredients here, first we can show that the likelihood function that we showed in the previous slide is always convex. And the reason for this is that my drawing app is performing unreliably, so I'm gonna lay off on it a little bit. The reason for this is that basically the form of the Hessian, if we go back a slide, if we go back a slide, the form of the Hessian, so if you take another derivative, another gradient here, the form of the Hessian is essentially going to be, rather than a difference of expectations of these random variables, it's going to be a difference of variances. Or it's going to be, sorry, just the variance of each random variable. And so you can, that's obviously always going to be positive semi-definite at least. And so you have kind of normal convexity that always holds. But that's not good enough to show that you efficiently recovered the true parameters. And so what we need is we need to assume that some guarantee of a constant probability of a sample from the true parameters falling into the set S. So what this corresponds to is saying that like my true parameters are not so far away from the set S that like that I very rarely see samples. I need like my set should have at least a constant mass under the true parameters mu star and sigma star. Once you have this guaranteed constant probability guarantee, you can use it to construct an efficient projection algorithm. So now that I have this assumption that like my true parameters always have probability alpha of landing inside S, I can basically project to the set of all parameters that have constant probability of falling into the set S. And in doing so, kind of restrict my search space. And I can show that within the search space, so within the set of parameters with probability at least alpha of falling into the set S, I have a strong convexity guarantee. And so the last missing ingredient to show that we can actually execute SGD here is we need to show that we can find a good initialization point. So if we can initialize inside this projection set, then we're all good because we can initialize inside the projection set and then just execute projected gradient descent using the gradient step we got on the last slide and the projection algorithm. And so what Daskalakis et al. Show is that even if you use the sample mean and sample covariance of the truncated samples, although those are not actually the true samples, they're a good initialization point. So they'll have a constant probability of having samples land in the set. And so the result, when you put all of these ingredients together, is an efficient algorithm for recovering parameters from data from a truncated Gaussian. Okay. Sorry, my drawing app just completely closed, so I'll just stick to the mouse and keyboard for now. Okay, so that was kind of the simplest, like a pretty simple estimation problem that's very clearly affected by truncation, but parameter estimation is not the only setting where truncation can affect things. And in fact, a much more relevant setting, even in practice, is truncation bias in regression. So like the Baker example, I'll give a really simple example of how truncation bias in regression can hurt us. And then I'll briefly talk about algorithms for dealing with it. So let's say our goal is to, we have a bunch of people and we know their heights and we have some measure of their basketball ability Y, and our goal is to basically figure out what the effect of being tall on being good at basketball is. And so we, to solve this problem, I guess we might go on like our favorite data repository and find a giant database of all NBA players who've ever played and basically do this regression and try to figure out, do some kind of regression and try to figure out what the trend is. And so we might expect something like this, where as you get taller, you get better at basketball, but obviously it's not like a strict relationship. There are some short people who are good at basketball and there are some tall people who are not. The interesting thing is that what we get is actually a very, very small or even null effect of height on basketball ability. And the reason that we're getting this small or null effect is because the data that we're looking at is already conditioned on players being good enough to play in the NBA or to get into whatever data set we're using. And so this is a classical example of truncation bias in regression, and it's also commonly referred to as an example of selection bias in causal inference, if I'm not mistaken. And so the generative model of this data, similar to our Gaussian example, is that we basically model ability as a function of height and some other random effects that we're not going to model. That ability then translates into a property of whether or not they play in the NBA. If NBA is yes, then we observe them. If NBA is no, then we don't even know that that player was sampled. And the truncation aspect is that we're only observing the players that are good enough for the NBA. Okay, yeah, so here I have a couple of really classical examples just to show that truncation is actually a really old problem that arises in many settings. So this is a famous study by Hausman and Wise in 1977, basically talking about a series of studies that tried to model the effect of education level on earnings. So they had some measure of education level, whether that be some kind of test or whatever, and they want to see how how important that performing well on that test is for predicting earnings. And they're specifically interested in this for for low wage workers. And so what they did is they picked some wage cutoff L, then only considered the workers who made less than $L an hour, and plotted the the relation between the education level and the income for these low wage workers. And what they found is this dotted line here that says estimated line above it. But what Hausman and Wise notice is that because of this truncation mechanism that you're enforcing on your data, the line that you're getting is actually a biased version of the true line, which is in solid color. So this is kind of a flipped version of the NBA example. Another similar study was done by Lin et al. In 1999 that basically was looking at correlations between income and child support payments. And what they found again is that even though previous studies had found one thing, they basically found that previous studies were affected by this bias where the amount of child support accurately predicts whether or not someone was going to reply to the surveys put out by prior work. And what this means is that you don't actually observe an unbiased sample of Y. Instead, Y is going through some truncation mechanism where if someone pays too much child support or no child support, they're probably not responding to your survey. And so obviously this being an old problem, there are many kind of classical statistical or econometrical solutions. And so what I'm going to be talking about today is basically trying to develop a unified and efficient algorithm for solving these kinds of problems. Okay, so just like in the Gaussian setting, I'll briefly talk about what the problem setup is. So again, we have some covariate X. Now it's sampled from either a finite set of covariates or some arbitrary distribution D. And now instead of just truncating based on X, we're first going to put X through a latent variable model. So what this means is that we have some true model H theta that we're going to pass X through, and then we're going to add noise to this latent variable from some distribution that we'll leave general for now. And then we're going to perform this the truncation mechanism we talked about earlier, but now based on the value of this latent variable. So we're going to assume we have some truncation function phi, where with probability 1 minus phi of z, we're going to throw away the covariate and the latent variable and restart and never tell the learner that we even sampled it. Otherwise, with probability phi of z, we're going to take this z, optionally project it to some hard label y, or just leave it be, and then give the learner access to the sample x comma y.
So, and just so I understand, so in the earlier setup, phi of z was always just 0 and 1, 0 or 1, but now you're allowing it to take other values.
Yeah, that's true. So actually, in terms of like the theoretical stuff we're going to prove, still going to leave phi of z as a hard function, just because without imposing some kind of constraints on phi of z, you can show that no estimation is possible ever. Okay. But it's possible that like if you put more constraints on phi of z, you're able to get something better, and I'll talk about that in the future work too. Okay, so let's talk about parameter estimation under the setting. So again, our generative model looks something like this, where our yi is sampled from a projection, an optional projection pi of the xi fed through the latent fed through like the true model, added to some noise, where noise is like from some distribution, and what we're looking for is an estimate theta hat for theta star. And again, just like the Gaussian setting, a standard approach here is just to maximize likelihood. So what does this likelihood look like? Instead of just being the likelihood of a normal distribution, now you basically you're integrating over all possible values of z that could have resulted in the y that you observed. So in the hard label setting, this would be like integrating, like if your projection operator was like 1 if z is positive, 0 if z is negative, then your integral is over the positive reals. So you're integrating over all possible z's that could have resulted in this y, and what you're integrating is exactly the likelihood of that z under the noise model dn. And so the reason I left this pretty general up till now is that we can actually kind of, by setting different variables here to different distributions and functions, we can kind of recover a couple of standard settings. So if assume that h is a linear function instead of just being an arbitrary function, then what we can recover is if we just omit the projection operator, so we make it the identity function, and then we make epsilon kind of a standard normal, then our maximum likelihood estimate, it corresponds to doing ordinary least squares regression, because the latent variable model is just like yi sampled from theta tx plus epsilon. If we keep the same noise function, but now we change the projection function to the one I mentioned earlier, so 1 if z is positive, 0 if z is negative, then what we actually recover is probit regression. And if we leave that normalization function, if we leave that projection function, but change the noise function to be the logistic distribution instead of the normal distribution, we recover the logistic regression estimate. And so just by kind of playing with dn and the projection operator, we can recover a couple of standard settings. And maximum likelihood estimation, like maximizing this likelihood I have here, exactly corresponds to doing each of these three regression techniques. Okay, so what happens in the truncated case? Okay. So again, just like in the Gaussian setting, the main idea here is that we want to maximize the truncated log likelihood rather than just the log likelihood. And so here I've restated what the normal likelihood was, just for reference. And so now in the truncated setting, what we have instead is we're now integrating not just over all possible values of z, but now we have to integrate that with the probability of even observing z. And then again, we have this normalization function that ensures that this integrates out to 1. And so in the setting, like Arnab mentioned, in the setting where phi of z is like a set thresholder, so like 1 if z is in S and 0 otherwise, then this becomes like the top term becomes the integral of z over like the intersection of pi inverse of y and S, and then the bottom one becomes just an integral over the set S. Yeah, and sorry for having to explain this in English. If I had my writing app still, I'd write this down. Okay, so what we can show is that just like in the Gaussian setting again, just kind of like taking the gradient and using a bunch of like standard derivative rules, what we'll find is that we again can access an unbiased estimate of the gradient of this function just using truncated samples. And so I was planning to write this down with a pen, but the idea is very similar in the sense of the gradient ends up looking very much like the gradient did for the Gaussian setting, where we have like the true data minus the expectation of the true parameters. And so what this leads to is another SGD-based algorithm. And so we might hope that we can basically take the exact same steps as in the Gaussian case and prove that all of these algorithms converge in terms of their truncated log likelihood. The problem that we run into is that the loss for some of these settings can actually turn out to be non-convex. So I will show an example of this. So here I've plotted the log likelihood for a really simple logistic regression setting. So here I'm assuming my phi of my truncation function is just truncating to a set between -1 and 3. On the x-axis, I have the value of the parameter theta, it's one-dimensional. And on the y-axis, I have the log likelihood. And as you can see, this is not a convex function. And so we're not going to be able to prove that it's strongly convex and like use the same analysis as in the Gaussian setting. It turns out, I should say that it turns out that in the linear, like in the case of linear regression, so if you're not doing classification, you can actually show that this is strongly convex and everything works as normal. And Daskalakis et al. 2019 actually proved convergence for linear regression using strong convexity. But in this general setting where you're allowing for a projection function and you're allowing for a more general class of noise distributions, this isn't true. So instead of using convexity, we might notice that the function above is quasi-convex. And so what we're going to use is, what we're going to use to prove convergence is a quasi-convex analysis. And so just to define what quasi-convexity means, for a function to be quasi-convex, we must have that basically for all points, y and x in the domain of the function, if we have the f of y less than f of x, then basically the gradient at x has to point towards the smaller value. And so this is just one definition of quasi-convexity that I like. There are other definitions. I think the most famous one is that like, if you linearly interpolate between 2 points, it can't be bigger than the minimum of the 2 points. Like it can't be smaller than the minimum of the 2 points. But I like this definition just because it's in terms of first order constraints, which are nice to deal with. So we're not going to use exactly the definition of quasi-convexity, but we're going to use a cool result from Hazan et al. In 2015. And Hazan et al. Defined this notion of strict local quasi-convexity. And this is a property that's very similar to convexity, but made a little stronger in one place and a little weaker in one place. So for a function, so they define a function to be SLQC, strictly locally quasi-convex, if, okay, I'm gonna try to do this again without writing, this inner product gradient of f of x by y minus x, if we can bound this away from 0, not just like less than or equal to 0, if we can A, bound this away from 0, but B, not necessarily for all points x and y, we only care about the case where y is in some small ball around the optimum. So if we can show that basically the gradient at many points x points vaguely towards the optimum, then we call the function strict locally quasi-convex. It's a mouthful. And the cool result that Hazan et al. Show is that although we can't really say anything about SGD in this situation, we don't have good convergence, we can say something about normalized SGD. So they prove that if you execute normalized SGD, which is just SGD where you take each gradient and divide it by its norm, like make it norm 1, normalized SGD with some minimum batch size, so you can't do one sample, will converge to the global optimum of SLQC functions, strictly locally quasi-convex. And so using this tool, we can basically show that, like step 1 will be to show that this general class of likelihoods that we've come up with, these truncated likelihoods, are SLQC, and then we can just execute normalized SGD to find the true parameters. Yeah, so I've already said this.
What is the actual result? So this is for what kinds of distributions and what sets?
Oh yeah, so I'll say that in the next slide. This is just like setup basically. Right. Like these properties by Hazan et al. Are just like, they're just proof for SLQC functions. I'll talk about like how we use that here. And so yeah, just to answer the question, what we can actually show is that if we restrict the settings to the ones we described earlier, so linear regression, probit regression, and logistic regression, and we restrict the truncation function phi to be some set S, and just like in the Gaussian setting, we have some kind of minimum probability, like constant probability guarantee of samples lying in the set S, then we can show that normalized stochastic gradient descent is going to recover the true parameters under this under the specified latent variable model. So as I mentioned earlier, you don't need quasi-convexity to show this for linear regression. Ilyas et al. 2019 already show it, that it's strongly convex and that normal SGD works fine. But we can show that normalized SGD is going to converge across these settings. And so just to reiterate what the setting looks like, in the simple case where S is an interval, which doesn't necessarily have to be true, what the setting looks like is basically we take X, we pass it to some linear model, we sample noise around the linear model, so either normal or logistic based on whether we're doing linear regression, probit regression, or logistic regression. We truncate it to the set S. In this case, we assume S is an interval. And then in the case where we're doing probit or logistic regression, so in the case where we're actually doing classification, the projection step just corresponds to like labeling it as 1 if it's over 0 and labeling it as 0 otherwise. And under the setting, that's where we can get provable guarantees that in basically poly time, we can find, recover the true parameters. using this normalized SGD algorithm. Cool. Yeah, so I wanted to leave some time for discussion, so I'll go pretty briefly through experiments, but I mean, yeah, like I won't cover this too much. The main idea here is that if we generate synthetic data exactly according to the latent variable model, and then we run truncated regression in red or standard regression in blue, we find that truncated regression much more accurately recovers the true parameters, kind of unsurprisingly, even without, I guess, generating that many samples. And we did this for both synthetic data and also real data from something called the Million Songs dataset, where you can find very similar results. So this here is for logistic regression. Yeah, and I'm happy to talk about, if anyone's specifically interested in the experiments or the implementation, I'm happy to talk about that in the discussion as much as people want. Cool. So yeah, I wanted to have time for discussion and also to go over the what I think are the cool extensions and limitations, and also future work relating to truncated statistics. So I'm sure Yannis is going to talk about this next week, but one really cool extension that he showed is basically we showed here how to estimate the parameters of a truncated Gaussian. What Yannis and Nagarajan show is how to estimate the parameter of a mixture of two Gaussians under this truncation mechanism. So we assume like a half-half mixture of a normal centered at mu and a normal centered at minus mu. And yeah, it should be noted that they prove global convergence of expectation maximization, which is actually pretty tough because global convergence is annoying to prove even in the untruncated setting. And so what they show, and yeah, correct me, is global convergence of expectation maximization on the truncated version of this problem. The other cool extension is throughout the presentation, I've kind of assumed that we have oracle access to a set S, where we can just ask like, would Z be an S? But this isn't always the case. Usually, like, you can trust S to be in some class of sets maybe, but assuming that you know it, that you have query access to it, might be too ambitious. And so this is exactly what Contanis et al. 2019 try to tackle. So it should be noted that if I allow the truncation set to be general, and I don't give myself query access to it, then estimating parameters is going to be totally impossible. And this is proved in Daskalakis et al., and it's pretty straightforward to see actually. What Contanis et al. Do is they show that if we assume that S is in some space of sets that has bounded complexity, so they consider both VC dimension and Gaussian surface area, which is another measure of complexity, they basically show that you can concurrently learn the parameters while learning the set S. And so they show a couple of sample complexity guarantees here on the right for a couple of like classes of sets S. And while these obviously are no longer polynomial in the dimension, it's a really promising direction of what if I don't actually know exactly what my truncation mechanism is, but I'm willing to make some assumptions. Finally, there's really recent work from Daskalakis et al. With a student in our group who tackled this problem in the dimensional sparse setting. So there, we assume that like we're doing linear regression again, but now the covariates are super high dimensional, but we also know they're k-sparse. And so what Daskalakis et al. 2020 show is that using some modified lasso algorithm, just like how we used, like deriving it using the same kind of techniques that we use for SGD, you can recover the parameters under truncation with error root k log d over n, which turns out to be optimal. Which time do I have? Okay, yeah. So in terms of future work, I think that the field, there's still a lot of interesting open problems that haven't been tackled at this point. So I'll talk about only a few, but I'm curious to hear also what other people think or see connections to. So one big thing is measuring and measuring robustness of these algorithms to model misspecification. So the work by Kantonis et al. About learning the set is definitely kind of work in this regard, but there's also many other kinds of model misspecification. So what if my latent variable model isn't exactly like logistic regression, but something else? How robust am I theoretically to this model misspecification? What if I have Oracle access to S, but Oracle lies some percentage of the time, either like randomly or adversarially? How well can I still estimate my parameters? And so in general, like the robustness of these algorithms, I think is still a very open question. There are also something I'm personally really interested in exploring is how this connects to causal inference. I mean, obviously, like truncation is really, really related to the whole field of how to deal with selection bias. But I think the connections could run even deeper than that. Another kind of potential application is in truncated outcomes. So you have many studies, at least that I've read, and I'm still new to causal inference, of studies where the outcome is truncated by some event causes non-response. So whether that's like death in a medical trial, or students dropping out in a study of like the effectiveness of an education intervention, or people not responding to surveys or not being asked. All of these are kind of possible connections I could see with truncation, although I don't know to what extent the methods here could help. The third thing that I think is a really interesting direction is whether or not we can use these techniques to improve current algorithms for censored statistics. So censored statistics is a closely related field to truncation, where I have the added benefit of actually observing when a sample lies outside of the set. So this is really nice, where like instead of just seeing samples conditioned on S, my sample generator will now tell me like, by the way, I sampled this X, but I'm not going to tell you the Y because it was outside of the set. And that way you have all of this extra information about what is in the set and what is not in the set. And there are many like classical econometric techniques for solving these kinds of problems. And obviously any algorithm for truncated statistics also will work for censored statistics. But the interesting question to me is whether or not you can get better algorithms for censored statistics using the same machinery or methodology. And I think that's all I have. So I'll go back to play. Yeah, but I'd be interested in hearing people's thoughts.
Okay, great. Thank you, Andrew. It was a great talk. Yeah, so if you have questions, maybe just speak up. Questions, comments. Okay, so maybe then I'll go first. So again, great talk. Yeah, I loved. I mean the whole. I mean, like you gave an overview of the. Of the layout of the area. So just two comments. So one is like for the sparse regression. So Yanis, I, and our two co-authors, we actually also have a paper on high-dimensional sparse linear regression and high-dimensional sparse Gaussian regression. So that came out like about a month before Costas's paper. So we gave. You might want to look at it. So it's basically. We look at the same problem, but we don't. So there are like a few differences. So they look at L2 recovery of the parameters, whereas we are trying to do. We are actually trying to do L infinity estimation. So like trying to recover the structure. But on the other hand, we have sample complexity bounds and not computational. Like they're not computationally efficient, but sample complexity.
Gotcha. Yeah, I'd be really interested in reading it actually, if you can send it.
Yeah, it's on archive.
I'll make sure to add it
from
to
our
the. Okay.
the other thing I wanted to,
great.
so about causal inference, right? So yeah, I agree. I mean, there are very interesting connections, which I think, hasn't been properly mined so far. So one thing I wanted to point out, okay, two things, right? So one is, so there's a paper by Judea, Pearl, and Barenbaum, and like others. So what they, their attitude is that basically selection or truncation basically depends on another variable. Okay, so they describe. So just like what you had, like for example, the NBA height is, so there's truncation. So there's like a variable which determines whether the truncation is happening or not, whether you get to see the sample or not. And that variable is like another node in the causal graph. So basically there are, so each variable depends on others through this causal graph. And then there's an extra node in there which determines whether you get to see that sample or not. And that, so like basically, so then there are, so that node is a function of other nodes. And you can ask, so for some kinds of dependencies, like for example, say you have two variables x and y. So there's an arrow from y to x, and the selection variable only depends on x. It doesn't depend on y. So in that case, truncation is trivial because it doesn't matter. You get to see some, but like the dependency between y and x is not affected by the truncation. But on the other hand, what you talk about is where the selection variable depends on y, right? So selection depends on y, which is the outcome variable. But in general, you can have like a high dimensional situation where you have like n variables, and then the selection variable depends on some of them. And like Pearl's work, what he does is he gives some graphical criteria on this whole graph, which determines when it's possible to compute, say, expectation of y given x just from samples. So without any assumption about the distribution. So here you have to make assumptions that the distribution is Gaussian or make a parametric assumption. So his work is basically like non-parametrically, like for example, in this trivial setting where the selection variable just depends on x, you don't have to do anything. But there are other situations where the selection variable could depend on y, but it could depend on other things in such a way that there is some algorithm, which is not the trivial algorithm where you just ignore the truncation. There is some algorithm which allows you to go from the truncated data to the untruncated, to finding out like the untruncated distribution, or at least the mean of the untruncated distribution. So I think it would be interesting to kind of combine these two different perspectives. So here, so what we are doing is basically more like a parametric perspective, like you assume you make a parametric assumption, but then you don't. I think there's a comment. So I'll put the link to the paper in the chat. So basically, you make a parametric assumption, but then you kind of treat the high dimensional distribution as like a black box, right? Like so it's some like high dimensional Gaussian distribution. But if you make assumptions about the precision matrix, so how, like the structure of the graph that defines a precision matrix, then maybe you can get stronger bounds and you can do other interesting things, right?
That's definitely, I think I've read the paper that is it like the one with the admissibility and like the separation? I can send, like, I think I have it open already actually.
Yeah, it's called Recovering from Selection Bias in Causal and Statistical Inference.
Okay, then I have maybe an older version of it because mine has a similar title, but
this is also not recent. This is from 2014.
Yeah.
Okay. And the other comment was
I think
that
the one
Yeah, the other comment was that, yeah, so in causal inference, people often want to estimate treatment effects, not just the mean or the covariance, but like what happens after an intervention. So I think that is also interesting to pursue in this truncated setting.
Yeah.
Yeah.
Actually, I'm curious. So in the I haven't read, like I read the one I sent, but not the one you sent. In this, like the more recent one, so like the recovering from selection bias one, is it an algorithm, or is it more about identifiability of the parameters, or
Yeah,
like
it is
of
exactly,
the
it is identifiability, but basically in the identifiable case, they have an algorithm which, I mean, it is an
Gotcha.
algorithm in the sense, yeah, I mean, like it's some function of the truncated data, but I mean, they don't give sample
Mhm.
complexity. It's just that it is a
Gotcha.
function. I mean, it's, yeah. Again, your work that you described using normalized SGD, is that public yet? Or?
That one will be public in like, it's at AI Stats. So
Okay.
I'm just working on like formatting stuff, and then it'll be online before that.
Okay, thanks. Okay, other questions? Yeah, the other thing was that this phi, right? I mean, I think that was also interesting. So I kind of missed what you said about that. So like, what kind of assumptions you need to make about phi of z?
Yeah, so I guess phi is mostly there for like for practical purposes. Like in all of the analysis we do, we just assume phi is thresholding to a set.
Okay. Does it really
But you
make a
can have
difference?
like,
I think I remember I thought about it a little bit, and it seemed that it's this. I mean, you can reduce to the 0, 1 case, like the threshold case, or
I think actually, like if you let phi be fully general, then it can completely change the problem. Like because you can make phi like proportional to any function you want divided by like some noise distribution, and have
so
it
if phi
kind of
is,
like,
so if the non-zero phi is lower bounded by some constant, then it is the same, right? Because you can just sample sometime and just
yeah, if you know phi, then you can just kind of like recover it.
right.
Then you can kind of recover the 0, 1 case again, I think.
Okay. But if you don't have any lower bound, I see. Okay. Got it. I see. But then, like your positive results, I mean, you just actually work with threshold and threshold.
Yeah, yeah, like phi is just 1 if x is in the set and 0 otherwise.
Okay. Any other questions? Okay, so thank you, Andrew. Yeah,
Great, thank you.
like the talk. If you could send the slides, then that would be good.
Yeah, I will.
Okay. 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 Thanks. Bye.
Great, thank you.
Thank you, everyone.